Okay, folks, this video, I want to discuss a question that I actually did not assign to you folks. Question 3 from written homework number 3. The reason I didn't assign this one, I mentioned in class, a couple of reasons, I guess. One is the exploration part was really good when I was in a classroom setting because this was really one where I think working in groups was helpful. This was an opportunity for folks to sort of help each other on the number line, splitting up segments into smaller segments, being really neat, counting up the segments properly. So unfortunately, I don't know that we could really recreate that setting properly through Zoom. Also, I was trying to kind of shorten the homework a little bit, so I didn't have you guys write up this question. However, this is an interesting question, and so I want to look at it a little bit. One day in class, I think it was like question 4 from homework 2, where you were doing a division problem, and without actually answering the question, you were trying to compare the answer to the value 1, right? So kind of a little abstract. And a student asked, "Is this what kids in school would do? Would they do it this way?" And my answer was actually, honestly, I wasn't quite sure that if they would do that at all. But then I was thinking about it, and my reply was that was sort of probably more challenging than we would ask students to do. However, for us to do as an exercise, just to basically practice our definition and also sort of push our knowledge to the limits, can be helpful. This problem is going to be similar. I doubt you would ever ask children to do this because this is really abstract. Ultimately, we want to sort of get a proof in terms of A and B. So random numbers, or I shouldn't say random, but abstract general numbers, not for specifics. However, it's going to challenge us to use the number line, practice our definition, get equal length segments, think about things like that. Sort of form common denominators, but by splitting up our number line, not just through any shortcuts. Okay? So the way the question read was, it said to choose two whole numbers, A and B, such that A is less than B. Okay? So A and B, and then what we're going to do is consider the two fractions, A over B versus B over A. All right, and then decide which one of those two fractions is closer to the number 1. So A versus B, closer to 1. All right, and so the way that I did do this in class was I had about 4 or 5 different combinations of A's and B's. And so different groups looked at different ones. Once they felt like they had it nailed, I would give them a second one. And between that we spent kind of a day like that, or half a day. And at the end, we put all of our results together. And what we saw was the same thing. One of these numbers was always closer, regardless of what we chose for A and B. Okay? The concept of choosing A less than B, if your numerator is less than the denominator, then this is what we're going to call a proper fraction. So examples like 1/2 or 3/4 or 2/5, anything like that. If B becomes larger than A, if your numerator is larger than A, we call those improper fractions. All right, and those values are always larger than 1. They're larger than 1 because if I've got, let me look at these reverses, 2 over 1. That means I had a whole. I didn't actually split it up at all, so I still have from 0 to 1 as my whole. But then I collected 2 of those segments, which means I would have jumped from 0 to 1 and then also jumped to 2, right? So that number is larger than 1. If I do this, and these are essentially reciprocals of one another, right? If I do this, that means I had a whole. I split it into 3 equal portions, but then collected 4 of those. So once I collect 3 of them, I'm at the whole number 1. The 4th one, I'm going beyond 1, right? So 1 and an additional third. And same idea. If I do 5 halves, that's well beyond number 1. So these are all going to be less than 1. These are all going to be greater than 1. The question, though, is which expression is closer to the number 1? Okay, so let's think about how we can start exploring that. So let's consider 2/3 versus 3/2. So that would mean A is 2 and B is 3. So let's say consider 2 over 3 and 3/2. And I want to see which one's closer to the number 1. Okay, so I want to set up a number line. And let's think about what I want to show. So I want to locate 2/3. I also want to locate 3/2, and I want to locate the number 1 because I need to consider that. So we always want to locate the 1 anyway. So let me put the 1 here. All right, and put a 0 right there. Okay, let me locate this guy first. It doesn't matter which one you locate first, really, but at some point we're going to have to start splitting our segments. Let me locate 3/2. So that says take your whole, establish your whole, step 1. Step 2, split your whole into 2 equal segments. So I'll split that in half. Okay? And then collect 3 of those segments. So that means 1, 2, I'm going to have to go another one of those segments over here. Right? And if I, is my board long enough? Let's say right to the edge maybe is hole number 2. So you could do that as well. If you have to split up beneath the 1 or beyond the 1, you could go all the way to number 2. But as long as we collect the same size segments, it doesn't matter. So I have my hole, split it into 1, 2 equal pieces for my denominator, and then collect the 1, 2, 3 pieces of that same size. And so that gets me to this thing over here. That's my 3/2. Okay. Now I need to locate 2/3 on my number line as well. And so that's going to require that I start splitting these original segments, right? Because remember, to locate 2/3, I have to split my whole, maybe like this, into 3 equal parts. But these red marks that I'm going to put, they have to live exactly where they should with respect to the black marks, all right? So if I need to split it into 3 equal pieces, that means once I start splitting up my original segments into small pieces, I want to be able to form 3 groups ultimately, right? So if I had 6 pieces all together, then I could form 3 groups of 2. So let me take these 2 segments and make those into 2 groups of 3. So kind of working in the reverse like that. So let me split each of these segments into 3 equal pieces by putting 1, 2 red marks in there, 1, 2 red marks in there, and let me keep going down the line. Because when I'm deciding ultimately who's closer to the number 1, I probably am going to want to count these small segments that I found. So I want those same size segments on both sides. So split that original black segment into 2 equal pieces. And this is kind of beyond what we need, but mine as well. Doesn't hurt, except waste some red ink. So there we go. Okay. Now I can locate 2/3. So actually, am I ready to locate 2/3? I think there's maybe one more thing I should do. So hopefully I pointed to the 3. If I'm going to locate 2/3, I don't want to just say I know 2/3 is 4/6. It's 1, 2, 3, 4, and locate 4/6, right? That might be where it lives, but I want to see the thirds. So to be able to form thirds, we had 2 original segments, so we split them up and formed 2 groups of 3 small segments, so 6 total segments or 6 small segments. Now we want to form 3 equal groups. So we want to do 6 divided by 3, division by grouping, and then so the result of that is 2. So I need to group up 2 little segments. So let's do my blue mark here, and then 1, 2, double up a blue, 1, 2, double up with that, and then 1, 2, and so forth. All right. Now I see 1, 2, 3 blue segments in my hole, and I can locate where 2 of them would be. So 1, 2 would live right there. Okay, so I didn't do any conversions of 4/6. I'm stating that because it kind of goes. And now I could label it 4/6 if I want to, but we don't really need to. Do I have to keep these blue marks going beyond the 1? So you could, but since 3/2 is over here, and then 2/3 is over here, there's really no need to do that at this point. As long as we've got the same uniform little segments everywhere, then now we're in good shape. Okay, we're ready to answer the question. Which is closer to the number 1? Well, and the reason why we can answer the question is because of these uniform length sixths, right? I've got 1, 2, 3, 4, 5, 6 pieces in my hole right there. I've got 1, 2, 3, 4, 5, 6 pieces in that hole. From 2/3 to 1, it takes 2 of these pieces. Let me put little happy faces right there, right? So 2 happy little segments gets me just to number 1. How many segments is the distance between 3/2? Let me use little sad faces here because they're too far away. Right? We see 1, 2, 3 segments. Three of those segments here, 2 of those segments. All those segments are the same size, so fewer of the segments is the closer number. All right, and that's really it. So all we've got to do is accurately locate these 2 fractions, and by accurately locating them, we're splitting the entire whole up into more pieces than either of these denominators tell us to do. Right, but once we get those equal size pieces everywhere, then it's just a matter of counting those pieces. Okay, so in this case, for 2/3 and 3/2, 2/3 was closer. So point for the proper fractions. All right, so let me do like a little tally up here. I'll keep that just a 1 because this one example, A over B is closer. Okay, will that always be the case? Who knows? I think I mentioned that when I did this in the class, the result was always the same. So spoiler alert, but let's figure that out. Let's do some other examples. Okay, so let's try, what's another good one? Maybe let's try 3/5 versus 5/3. All right, just to practice setting these guys up on number lines and how we would do that. Okay, so first let me locate, last time I located the improper fraction first on the other side. Let me do that again, actually. And I don't know that it really matters. Maybe next time I'll change it up. The reason why I want to do that is since that's beyond 1, I kind of want to make sure that I don't like have to go onto my door over here or onto the molding of my door. I want to keep everything on the board, right? So I want to locate 5/3 based on this hole. So that means split that hole up into 3 equal pieces. And then keep going with those size pieces, right? So another 1, 2, 1, 2, 3 of those pieces. Again, if you like, maybe get the next whole number. That might be a good idea if you're struggling with keeping these sizes the same, or if you just really want to see that we've got thirds. Maybe for all of these problems, we would want to go over to the next whole number. Okay, so now I see 1, 2, 3, 4, 5, 5/3. Okay, again, 5 of them we can count the 5 segments. Why are they thirds? Because 3 of them make up a whole, right? So our whole is split into 3 equal portions. That's what these portions are. Cool. So we located that. Now we have to locate 3/5. So what do we always do here? I've got 1, 2, 3 segments. I need to be able to form 5 groups of small segments. So I need some number of small segments that will work. And so what usually seems to be the way to go is take the original segments and split each one into this many smaller pieces. Okay? Let me just mention that will always work, but sometimes you don't have to do that. If these numbers had something in common, like a 4 and a 6 are both even, you might not have to split all the way. Maybe I'll do an example like that. Although I don't know if I can do it with these problems. Okay, anyway, let me split each segment into 5 little pieces. And what I'm going to do is form 3 groups of 5, which is 15 small pieces. All right, that's my goal, because then 15 I can make 5 equal groups. So if I want 5 pieces, that's 4 little lines. So 1, 2, 3, 4 red marks. 1, 2, 3, 4 red marks. And 1, 2, 3, 4 red marks. Okay, and then where did we go in the previous problem? We extended those marks further because ultimately I'm going to need to count them up on this side as well. So let's go 1, 2, 3, 4 little marks. 1, 2, 3, 4 little marks. I don't know that we need all these. All right. Okay. And so now, let me, again, locate 3/5 by showing fifths and then locating that. So if I want to show fifths, that means I want 5 groups. So how many little segments do I have to collect? Well, I've got 15 pieces together, and I want to form 5 equal groups. So if we do division by grouping, 15 divided by 5 gives me 3. All right. You notice it's always like the 2 factors, right? So that it shouldn't be surprising, but just if we don't know, or if we just want to say, well, wait a minute, how do we know? Now we know. Okay. So let me collect 3 pieces together. So 1, 2, 3 little segments. 1, 2, 3 little segments. 1, 2, 3 little segments. 1, 2, 3 little segments, and finally 1, 2, 3 little segments. So now I see 1, 2, 3, 4, 5 segments in my hole, and I can collect 1, 2, 3 of them and locate my 3/5. All right. Same as our previous problem. Do I need to put the blue marks over here? There's really no reason, because I'm not locating any number of fifths beyond the 1, so I don't need to show this hole being split into 5 equal segments. If you want to, you could, but we don't need to. What we need to do now is, again, just decide which is closer. And the great thing is that these little segments, these red ones up here, are the same size as these little segments over here. And so since we're got the same size segments, we just have to count the amount of segments. So here I see 1, 2, 3, 4, 5, 6 little segments. All right. On this side, I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 little segments. Okay. more segments means this guy's further away than this one is. All right. So that's another point, let's say, for the proper fraction. Okay. Proper fraction is closer again. Okay. What time is it? 15 minutes. Should we do a third example? Maybe I'll just challenge you guys, if you are not convinced of this example, maybe try to, you know, do one or two examples on your own, see if it works out. Okay. Ultimately, what we would like to do is, if we claim, let's say we do enough of these examples. Remember, we can't prove anything by mere examples. In other words, I could do 1,000 of these examples. That's not a proof that the A over B will always be closer, right? That's just sort of evidence, but that's not a proof. If I wanted to prove it, I have to do it in terms of A and B, right? How would I do that? That gets a little bit challenging. Let me sort of brainstorm that idea on the board here and see if it makes sense. Okay, so let me put a 1 here, 0, 1. All right, and let me put the 2. In reality, sometimes putting the 2 might not even be enough, because this improper fraction, right, if I had 2 sevenths, right, then its reciprocal is 7 over 2. That's even beyond the whole number 2, right? So I'm not guaranteeing that the improper necessarily lives between 1 and 2, but maybe just to visualize things, get a extra, pretty good, get a extra whole number on there is okay. Let's just brainstorm how we might do this, okay? So to locate the proper fraction, A over B, that means I need to split this whole into B little segments, right? And so the way I've done this in the past is kind of use ellipses for that. In other words, if I just draw some number of lines, and you can count it and say, wait a minute, though, this isn't general, this isn't abstract, the B is actually some whole number. Okay? So let me kind of do that, and let me put some dots in here. Right? So I'm actually kind of erasing a portion of the line. And I've got something like that, right? So I see some number of segments here, and then I'm not sure how many are missing, right? But I know that there's B of those little segments. And so to indicate that, let me write B over B, right? I took my whole, I split it into B. B is just a number, right? So B equal length segments, but then I collected all B of those segments. And so I'm back to the 1. Okay. And now if A is less than B, then that means A lives somewhere over here. Right? And again, if I put it here, then you could count back, but that's okay. Let me label it like right here, let's say. A over B. All right. I'm debating putting more ellipses here. Let me put my A over B, either way, it doesn't really matter. Let me squeeze in some more ellipses here. All right. Why am I doing all that? I don't want to be able to count how many segments A is from the 0, and I don't want to be able to subtract backwards how many segments it lives right there, right? So I'm really just trying to mean that this is somewhere in the middle here, okay? Okay, the question now is, what's this length right there? What's that distance, right? In other words, how many segments would I have in here? Well, that's sort of like a missing factor, because or missing addend, because if I started with A over B, right, and then I added some number of these pieces are B size, you know, from splitting my whole into B equal pieces, and then I get to B over B, right? So if I start here at A over B and end up at B over B, how many additional segments did I have to go in here? And it's going to be B minus A, right? Whatever that number may be. Alrighty, and how do we do that? Well, if I'm collecting these things all together, then we kind of argued a little bit. We can add our numerators because the B is just describing what we've got. And so if you forget fractions for a moment, if you are adding from 107A, you take A plus B minus A, right? What does that do? Well, these parentheses are visual there, but we really don't need them. So that's A plus B and then minus A. A minus A is 0, right? So that cancels itself out, and so the answer here is B. All right, and so if that's happening in our numerator, that means I could, if I want to represent it as a fraction, this length, I could do that. or I could just count up the number of pieces that I've got. So let me phrase it like that. So there are b minus a, that's just some number, b minus a pieces between this number a over b and my whole number 1. All right, so again, that's just telling me how many pieces there are. I explained it this way. Another quick example is, let's just say I have 1, 2, 3, 4, 5, 6, 7 pieces in my whole, and I locate 4/7, and then I want to know how many pieces are left here, right? Well, if I do the subtraction, or the missing addend is 1, 2, 3 pieces, so 3/7, or just count the pieces 1, 2, 3. That's this value 7 minus 4, right? 7 minus 4 is 3. That tells you how many you need to add there. So that's exactly what we're doing here. We're just trying to do it in the arbitrary sense. So there's b minus a pieces. The pieces themselves are, you could say, beats, though, right? So that the size of the piece is going to be relevant here. On this side, I located b over a. I split my whole into a pieces to do that. And let me show how that is going to work. If a is less than b, then that means I split my whole into fewer pieces than I did over here, which means the pieces will be larger, right? So the pieces are going to be larger over here because you could imagine that I split it between 0 and 1, but since this number lives between 1 and 2, let me split that whole into larger pieces. So let's say a piece like that, a piece like that. Throw some ellipses in here, those dots to kind of give some kind of spacing here. A piece like that, and then a piece like that, and maybe a couple more ellipses. Oops, and let me just do it like that. Okay, so what am I trying to show here? I'm trying to show that the pieces here are larger than those pieces, the pieces on this side. And again, how do we know that? Because a is the smaller number. And so if I break a whole up into a smaller number of pieces, those pieces are larger, right? We use that argument a lot on written homework 1 to compare different fractions. B over a lives somewhere over here. Let me locate that fraction right there. And again, I'm putting it on this side of some ellipses because I don't want to be able to count and just say, oh, it's just 1, 2, 3 segments, right? So in these dots, there might be more maybe this is much more spread out than we can see right here. Okay. So I've got b over a pieces, and now I need to see how many pieces live between here and here. All right, so that's a little bit tricky. What did I do here? I split this whole from 1 to 2 into a. A is just some number. I split it into a pieces. A is telling me the number of pieces. I can imagine that if I split this whole from 0 to 1 into a equal pieces, and collected all of those pieces, then I split the whole into, so I'm not showing that I did this, but I could imagine or brainstorm that I split my whole into a equal size pieces, then collected all a of them, right? That would get me back to the 1. Okay. So how many pieces now live between the 1 and this mark, b over a? The reason why I needed to do that is because now I'm going to look at these two things that have the same denominator. Right? Just like here, we were looking at things that had the same denominator because the denominator basically described the pieces. And then here I had a of the pieces, then I was up to b of the pieces. So how many did I have in between? B minus a. Here I've got a of the different size pieces, right? But I've got a of the pieces at my 1, and here I have b of my pieces. So how many blue pieces are there in between here? Same amount. There are b minus a. So again, that's a number. So that's just saying like there are 4 pieces or there are 5 pieces. There are b minus a pieces between 1 and my number b over a. Okay? So whatever the difference is between b and a, if you subtract them, that number when you subtract it tells you how many little pieces you have to go here to get from a over b to there. And it also tells you how many large pieces you have to go sort of either from 1 to here or sort of to backtrack from there. Okay? So how does this draw our conclusion? Well, it's the same amount of pieces. All right? If we consider those original pieces, it's the same amount. However, and I argued this in terms of this relationship right here. But since A is smaller, then when we split our whole into A pieces compared to B, those pieces end up being larger. So we've got the same amount of pieces here, but we've got larger pieces on this side. And so if you count up the same amount of large pieces, that's going to be a larger distance than this amount of tiny pieces. All right. That, you know, probably I could include a couple more details with written words there, but that really gives us a proof why in our two examples, A over B was always closer. That's always going to be closer. All right, and here's our proof of that. And what it really comes down to is the number of pieces on either side, and then the size of those pieces. Alrighty. So when we did that with concrete numbers, when we did that with the actual examples, we ended up abandoning these original pieces and finding smaller pieces altogether, right? Like getting that common denominator. We did not do that here. All right. But let me just kind of sum up the argument that we did do. Where's some not sunlight? Just real quick. 0, let's say here, and let's put a 1 and put a 2. So a couple whole numbers there. Let's think of the first example we did, which was 2/3 versus 3/2. Okay. To locate 3/2, we said let's split our whole into 2 equal pieces, both wholes. And then count up 1, 2, 3 of those pieces. That was 3/2, right? And then we said, okay, then let's locate 2/3. And so in order to locate 2/3, we had to split these segments up into smaller segments. All right? But ultimately, let me not do that on this side. What we did then is then form thirds is double up these marks. And right here, that green mark right there is 2/3. Okay? So with concrete numbers, and when I say concrete, you know, 2, 3, not the A and B. With those concrete numbers, I had to use that little red mark in there in order to locate 2/3 accurately. So I needed to use that red mark. However, let me get rid of it now. Right, that was a little tool that I used. Let me get rid of it now just to show exactly what's going on here. In this case, we compared A over B to B over B, so to 3/3, right? And 3 minus 2 is 1. And there's one segment in here between 2/3 and 3/3. Right? So B minus A, 3 minus 2 was 1. One additional segment right there. All right? So that's what's going on here. B minus A, however many additional segments we've got. Then on this side, what did I do? I wanted to consider this denominator. So notice here we had B over A, and then I wrote it A over A. So 1 is the same as 2/2. Right? 1 2/2 is the same as my 1. And so how much space is here now? Again, this is 2/2, this is 3/2. So how many extra pieces do I have to go? 3 minus 2 is 1, right? That tells me the size of this blue piece right here. Or that tells me the number of blue pieces, the amount of blue pieces I've got right there. Okay? So this shows exactly what we did up here, that you've got the same amount of pieces on either side, same amount of your original size pieces. Once you go splitting them up to accurately locate these fractions, which we need to do, you kind of lose track of where we were going with this proof. However, I see I've got one green piece here, one blue piece. This blue piece is larger than the green piece because the blue piece represented splitting our whole up into only 2 pieces. And so those were pretty large pieces. The green piece was we split that same whole into 3 pieces, and so we had smaller pieces. And so now if I'm comparing one small piece to one large piece, obviously the large piece is larger. Okay, folks. Happy I took that one off the homework, maybe. But again, if you were on the homework, you would have done a lot of numerical examples to sort of get the feel that this is going to be our answer. This sort of demonstrates a proof. I will not ask you to reproduce this if you're thinking that this is going to be on the exam using these ellipses right here to kind of prove it in general. That's really, really high level. If you can understand what I've done here, that's what I'm looking for. All right.